Hierarchical rule learning and generalization.
Alright, so my name is Denise Werchan, and I'm a second-year grad student at Brown University, and today I'll be talking to you about hierarchical rule learning in 8-month-old infants. So throughout life, we must constantly learn different rules for different contexts. So for example, a child may learn that when they're at home, they have to use their inside voice. Okay. And then they also must learn, for example, that they can't throw balls. Then by learning these different rules, children may group them together to form an abstract rule set, such as one for inside. And by doing this, gives children the potential to then generalize this rule set to novel contexts. So, for example, then when children enter school, they may be able, rather than relearning all of these same rules, they can instead just transfer their existing rule set to this novel context. So although this seems like a basic task, it requires several computational demands of the learner. So for example, for one, it requires the ability to be able to represent these different rule sets abstractly, such that they are not tied to the particular context that they were learned in, such as at home or in school. And then it also requires the ability to be able to cluster these different arbitrary contexts that are associated with the same rule sets together. And then finally, it also requires the learner the ability to then be able to build new rule sets when necessary. So let's say when a child is at a park, for example, they wouldn't want to generalize this rule set they already have for at home or in school, but they would instead want to build a new one. So previous work in adults has shown that adults will spontaneously and implicitly construct hierarchical rule sets without being instructed to do so. So when adults are given a simple task, such as learning associations between different stimuli and actions, rather than just learning these as individual associations, adults will instead learn them as hierarchical rule sets, where they will treat the different features of these stimuli in a hierarchical manner, where one feature, such as shape, may cue this abstract or hidden rule set, which then signifies simpler rules, such as between color and different actions. And so by creating these rule sets, rather than just learning individual associations, research has shown that adults can then use this to generalize learning in novel contexts. And then so there's also a lot of work from both computational modeling and neuroimaging studies that this type of learning in adults seems to be supported by interactions between the striatum and prefrontal cortex via dopaminergic projections. So this work from adults showing that adults will spontaneously create hierarchical rule sets, even when there's no need to do so, may suggest that humans are biased to kind of create abstract rule sets such as this. And one reason they may do so is that it's adaptive, as it affords future generalization opportunities, so you don't have to constantly relearn things in new contexts. But this type of learning hasn't yet been examined in infants, and we don't have a very good idea of what are the developmental origins of it. But the benefits of such a learning system for a naive infant learner are unambiguous. So for example, this type of learning may help infants raised in bilingual environments separate languages. So they may learn that when with mom is associated with an English rule set, which then signifies simpler rules between different objects and their labels. But then with dad may be associated with a Spanish rule set. And then by doing this, when they enter a new context, such as with grandma, if they see that some of these rules that grandma uses are also associated with a Spanish rule set, rather than relearning all of these same rules with grandma, they can instead just generalize this old rule set and immediately infer that all words that were associated with dad also should be associated with grandma and vice versa. So in the current study, we sought to examine whether infants will spontaneously create hierarchical rule structures such as this, like we know that adults do. And so what we did was we tested 28-month-old infants on a learning task and a generalization task that was modeled directly after adult work. So during this learning task, infants were presented with 4 different cue target location pairs. So these cues simply varied by both shape and color. And then these target locations consisted of an animated toy that was presented in 1 of 4 quadrants of the computer screen. And then so just to give an idea of what this task would look like for infants, so they would first see this cue presented on the screen, and then after a short delay, they would see the animated toy presented in the associated target location. And then what we did is we used eye tracking to measure the reaction time from the onset of this cue to the arrival at the target location. And we did this with the idea that if infants were learning these different pairs and beginning to predict that when this cue comes up, where the associated animated toy would play, then they would have faster RTs over time. And so in addition to that, we also decided to explore and measure eye blink rate, since there's some evidence that this appears to be an indirect marker of dopamine activity, so we wanted to explore whether there could be any potential relationships between this and learning in infants. And so one thing to note about the design of this learning task is that these different cue target pairings were symmetrical. And what I mean by that is that color and shape were equally frequent. And so because of this, there is no actual inherent structure in this task. And so this is important because then it allowed these pairs to be learned multiple ways without a bias for one way or the other. So for one, they could be simply learned as these individual associations between the different cues and the target locations, or they could be learned as a hierarchy of rule sets, where one of these features from these symmetry, such as shape, make you an abstract hidden rule set, which then signifies simpler rules between color and the target location, for example. And then, so since this design was symmetrical, if infants did learn in a hierarchical manner, then it's possible that they could learn with shape on top, as I have depicted here, or they could also learn with color as this higher order feature cueing this rule set. But based on some pilot work and the shape bias in this age group, we suspected that if infants did learn hierarchically, then they would be more likely to do so using shape as this higher order feature. So next, after the learning task, infants immediately went on to the generalization task, during which they were presented with 2 new shape contexts. So one of these shapes were associated with a rule set that contained the same rules as a previously learned rule set. And then the other one was associated with 2 rules that both had been experienced before, but across different rule sets. So therefore, this consisted of an entirely new rule set. And so what we hypothesized is that first, if infants learned simply individual associations without inferring this hierarchical structure, then during generalization, we should see no difference between these different shape contexts because they would not have any prior learning to be able to generalize to facilitate learning. But if infants did form hierarchical rule sets, then we expected that we would find faster reaction times for the matching rule set compared to a novel rule set, since infants would then be able to transfer learning of this previously learned rule set to this novel context. So we found, so first looking at the reaction times during both learning and generalization. So first during learning, we found that infants' reaction times significantly decreased with trial exposure, so indicating that they seem to be learning these different cue target associations. And then during generalization, interestingly, we found that infants were significantly faster on this matching rule set compared to the novel rule set. So providing evidence that infants did appear to learn these associations as a hierarchical structure, and then were able to reuse this to support learning in a novel context. So although this provides the first evidence that infants are building this hierarchical structure, we wanted to see if we could find any further evidence of this. So first we decided to look at higher order rule switch costs. So based on work of adults, that shows that when adults are much slower when the higher order role switches from one child to the next compared to when it stays the same. And then again, we also wanted to explore any potential relationships with eye blink rate, since there's some work showing that eye blink rate is related to updating mechanisms and rural learning tasks, and since there is some indirect evidence that eye blink rate is also related to dopamine activity. So first, looking at role switch versus repeat costs. So we calculated two different costs. First, we looked at a shape switch cost, which is simply the average reaction times on trials for the shape change from one trial to the next, minus the average reaction times on trials where the shape repeated. And we also did the same thing for color switch costs. And so we predicted that if infants had formed a hierarchy with shape on top, as we suspected, then we should observe a significant cost to shape switches. And indeed, that's what we found. So we saw that the majority of infants had a significantly higher cost to shape switches compared to color switches, and that this was above 0, so indicating that, providing further evidence that they did learn this hierarchical structure. And then so next we wanted to explore relationships between learning and eye blink rate. So now we decided to explore blink rate during role switch versus role repeat trials. And so we found that, so during the first half of learning, when these role sets were just beginning to be formed, we saw no difference between eye blink rate during shape switch versus shape repeat trials. But then during the second half of learning, when the role sets were now being formed, we saw that infants had significantly more eye blinks to shape switch trials versus shape repeat. So to summarize, so our results show that infants appear to build and reuse role set despite having no cues, patterns, or statistics that were relevant for them to do so. And then we found evidence of this both by seeing faster reaction times for a matching role set compared to a novel one, and as well as seeing significant reaction time switch costs to trials for these shape switches. And then we also saw an interesting relationship where infants actually had increased eye blinks on shape switch trials, which could potentially provide a clue that perhaps this type of learning in infants is supported by some of the same dopamine-dependent mechanisms that we know is supported by adults. So in conclusion, our results show that infants spontaneously create these hierarchical role structures even when they have no need to do so. And then we found some interesting evidence as well that raises the possibility that perhaps this type of learning is supported by the same neural systems as in adults, in particular dopamine-dependent mechanisms in prefrontal cortex, perhaps. And we're currently following up on this by exploring this idea using near-infrared spectroscopy, so we can actually see infants' prefrontal activation during this task to get an idea of whether this relationship of eye blink rate is meaningful. And so altogether, these findings add a new learning mechanism to what we know about the mechanisms infants have to learn about the world around them, by showing that they have an additional mechanism that can help them learn and generalize information, particularly in noisy or ambiguous environments. Right, and lastly, I'd like to thank my advisors and lab and everyone who helped me on this work, funding from an NSF Graduate Research Fellowship, and then of course all the infants and families who made this research possible.